Good morning. Today is an exciting day in Survey of Calculus. We actually get to start working with one of the most important concepts in calculus, which is finding a derivative. We've talked about the theory behind derivatives in Chapter 2, and we said that we understand the concept of a derivative, that it calculates the slope of the curve or the slope of the tangent line at a point. We approximated derivatives, and in our approximation, we came up with what we think is the derivative function for two popular functions. So, for example, our basic x squared function, g of x is x squared, we did by approximating and plotting points, we determined that the derivative is 2x. So we said that that quadratic function has a linear derivative. And then we made an educated guess that the derivative of the natural log of x is the function 1 over x. We will actually, we could actually prove that using the definition of derivative that was focused on in the focus on theory, excuse me. And we will talk more about derivatives of logarithmic functions in another section. But we also learned some new notation. We had what's called our Leibniz notation, or Leibniz actually, for a derivative. We're going to use that same notation as another way of asking for a derivative. And it's the notation where we say, let's say d dx. That means take the derivative of with respect to x, and then we might say, here's our function inside. So we don't really have any function notation, and we don't have any y equals notation. But we're saying, here's a function in here. This one happens to be linear. What's the derivative? Well, that is a linear function, so we actually know that derivative. We know that the derivative, that a linear function has a constant rate of change, so the derivative is the slope of that line. Okay, so the terminology we use for taking a derivative is to differentiate. So that's why we say we're looking at shortcuts or rules for differentiation. Okay, in the focus on theory assignment, you looked at using the definition of derivative, which uses the difference quotient and the limit as h goes to 0. So every derivative rule could be defined, or we could come up with all these differentiation rules using that definition, but many of them are very, very tedious, so we do not use that to find all of our derivatives. But we do have these shortcuts, which many of them can be proved using that definition or other rules. So let's move into section 3.1. Here's our section on derivative rules. And these are our basic rules. You will use these the most often throughout this course. The first two we already know. We already know the derivative of a constant. If I have a constant function, h of x equals -2. Okay, we talked about the fact that the constant function is the graph of a horizontal line. And we know that the slope at every point on the graph of that horizontal line is 0. So the derivative of a constant is 0. So here is what we would say is our rule. Very informal. The derivative of any constant, meaning just a number, is always equal to 0 because the graph has a slope of 0 at every point. Okay. We also talked about linear functions in the same respect, being that the derivative is the slope, which is the slope of the line or the rate of change. So for example, if I have the function g of x is, let's just say, a basic 3x, okay, which is a line, actually has a y-intercept of 0. Oops, this is not supposed to be here. There we go. This is g of x. and has a slope of 3, goes through the origin. So at any point on this line, the slope is going to be 3. So the derivative is 3 for any x value. Right? So that's another rule, basic rule we have. It's kind of a version of another rule we're going to talk about in just a minute. So the derivative with respect to x of any basic linear function is always going to be m, or whatever the slope of that line is. Okay, so let's expand to one of our most popular rules, and it's called the power rule. So basically, if I have a variable, it does not always have to be x. We'll start switching the variable up in a little bit. If a variable has a numeric power, and that power can be any real number, it can be a whole number, it can be an integer, it can be a negative number, it can be a rational number or a fraction, it could be a decimal. You can find the derivative by decreasing the power by 1 and multiplying the variable by the original power. So one way we like to say that is we say you're going to bring down the power and subtract 1 from the power. That's what the power rule says. Okay, so here's the rule. The derivative of x to a power, n just represents, we should probably say that, n is a real number. Okay, so the power rule says that we bring down the power, so the n comes out front, we bring it down, we multiply it by the x, or the variable, and then we decrease the power by 1. So the power becomes 1 less than it was. So let's look at some examples and some different notations that we will use for the derivative. If we have y equals x to the 4th, there's a couple ways you can do it. Some textbooks will say y prime. This textbook seems to do more often using the Leibniz notation, so dy dx. So the derivative of y with respect to x would be bring down the power 4 times x, decrease the power by 1, and it becomes 3. So the derivative of x to the 4th is 4x cubed. Okay, on B, h of x is x to the 29th. So we have function notation. We know what derivative notation would look like. That would be h prime. So we bring down the power 29, and we decrease the power by 1. 29 minus 1 is 28. So that would be the derivative of x to the 29th. Okay, and then we have our new notation for finding the derivative of x to the negative 5th. So now my exponent is not just an integer, or it's an integer, but it's negative. Okay, so here you basically don't rewrite anything. You're just saying, what do you get when you take the derivative of that? Okay, so we're going to bring down the power, negative 5. Now, here's where you have to be careful. You're still subtracting 1, so you have to be careful here. Negative 5 minus 1 is negative 6. Okay. On the others, we could easily do that quickly without writing anything down, and we can see that it's 1 less. Well, we're doing 1 less still, but we're going in the negative direction. Okay, so let's look at kind of extending these rules. What if I have a function times a constant? Okay, for example, I have x to the 9th, but it's being multiplied by 10. 10 is a constant. Okay, so what do we do with that 10? Well, the constant multiple rule says that the constant just goes along for the ride. So you're going to find the derivative of your function, which right now we know is x to a power. We'll find the derivative, and then you just multiply it by that constant. So it just comes along for the ride. So my derivative here then would be, basically we've got the 10, Okay, then we're going to take the derivative of x to the ninth. Let me write it down here. So the derivative of x to the ninth would be 9x to the 8th. Then we take that times 10. So what happens is I have 10 times 9, which is 90x to the 8th. So we're going to just go through that all in one step. We don't want you to have to write that many times. So ultimately, what do? You take the 9 times the 10. So we're going to take the power times the constant. 9 times 10 is 90, and then decrease by 1. You can do it all in one swoop. Okay? Now, sometimes the constants, it's a little tricky. Here, I actually have x to the 8th divided by 2. So this is not a constant multiple. It's not being multiplied by something. It's being divided. So we have to think of what would it be if it was multiplied by something. So I can rewrite that. You don't always have to rewrite it as long as you recognize what's happening. That's actually equivalent to 1/2 times x to the 8th. Okay, so I can pull out the 1 and the 2 and rewrite it as multiplication. Now I have a constant multiple, and I can find the derivative by saying, okay, what's 8 times 1/2, or half of 8, is 4, and then decrease the power by 1. So we get 4x to the 7th. So recognizing that these two are equivalent is an important thing to do. All right, so we're going to expand now. Another rule. Okay, we've got derivatives of sums and differences. So basically what this does is it expands our world to a whole bunch of different functions, specifically polynomial functions. So if I have a derivative of a sum or difference of functions that are differentiable, then all we have to do is take the derivative of each term, because we know they're divided up, the terms are separated by plus or minus. So let's say I have x to the 10th minus 7x cubed plus x squared minus 8. Okay, so here's a polynomial function, happens to be degree 10. All right, so my derivative then is basically, what's the derivative of x to the 10th? And x to the 9th. Okay, plus or minus, plus minuses add the opposite basically. Okay, so then we'll say, okay, what's the derivative of, we can think of that as negative 7x to the 3rd. So 3 times negative 7 is negative 21 x to the 2nd. The derivative of x squared, using the power rule again, is 2x plus 2x, and then minus 8. So that's a constant. This is a constant. What's the derivative of any constant? Notice there's no variable there, is 0. But do we need to write the 0? No. So basically our derivative would just be this polynomial function. Okay, so that opens our world up. So here's an example. What I'd like you to do is pause the video and you try this one. Okay, so to find the derivative, we're going to take 5 times 1/3, which becomes 5/3, increase the power by 1. The next term, we're going to take 4 times negative 6, which is negative 24, increase the power by 1, we get x cubed. In the third term, we notice that the exponent is a decimal, which is not a big deal. We use the same rule. So we take 3.4 times 2, which is 6.8. When I decrease the power by 1, I get x to the 2.4 power. all right, plus 2 times 0.6 is 1.2, x to the first. You know, you don't have to write that, okay? Now, this one's kind of tricky. You got to be careful here. This negative 18x, remember that's linear. So the derivative is the slope of that. That would be a line, negative 18x, if I graphed it. So that becomes minus 18. Now, if you're applying the power rule, a lot of people would want to think, oops, subtract 1, because let's write that out here. X to the first. If I subtract 1, I get negative 18x to the 0. Well, what is any real number to the 0 power with the exception of 0 is 1. So that becomes negative 18 times 1, or negative 18. Okay, so when there's just an x to the first power, then the derivative is just the coefficient. And then we know the derivative of this constant is 0, so we do not put that, although I'm going to just write it to make a note for your notes. So this would be the derivative of that function. All right. So now let's throw in what happens when we have some negative exponents, fractional exponents, and whatnot. Okay. Once again, even though this is not a polynomial because the exponent has some negative exponents, it's still a sum or difference of terms. Okay, so I just find the derivative of each term. So the derivative of x cubed would be 3x squared. The derivative of negative 3x, x to the first power, so it's linear, so the derivative is just the coefficient, or the slope of that line. Okay, now we're going to say, okay, power rule. Negative 1 times 2 is negative 2. Be careful, subtract 1. And we get x to the negative second power. Okay. Last term, we take negative 5 times negative 8, which is positive 40. Decrease the power by 1, and that becomes to the negative sixth. Okay. Now, you could leave this. You're trained in algebra. They say many times, don't keep negative exponents. So you could rewrite those two terms with a positive exponent, and sometimes that is nicer when you're plugging a number into the derivative, but you don't always need to. So you got to think about what are you going to do with that derivative. But if we rewrote those two terms, I rewrote this term, that would become minus 2 over x squared. So remember, when we want to get rid of the negative exponent, remember, it moves it down or to the other side of the fraction. So this last term will become plus 40. The 40 does not have a negative exponent, so it stays where it is. The x comes down and the 6 becomes positive. So if we wanted to write our derivative with no negative exponents, we could do it like this.